Welcome back. This is video lecture 2.2 that goes with the class on Wednesday, August 26th. The topic of today's video lecture is the physics concept of acceleration. Let me remind you that this video lecture is a summary only of the more detailed content that you can read in our online textbook on Wiley+. The book is named Fundamentals of Physics. And as we can see here at the top of our slide, the corresponding section for today's reading is Chapter 2, Section 3, where the concept of acceleration is introduced. Let me show you what that looks like if you log into the Wiley+ site. Right? When you click on Read, Study, and Practice on the Wiley+ site and choose from the Contents drop-down menu Chapter 2, Motion Along a Straight Line, which is the chapter we're studying, you get this page that you see before you now, and you click on, under Reading Content 2.3, Acceleration. Wait just a moment for the reading to load, and this is what you can read to get all the background explanations and definitions of the concepts that we're going to talk about, not to mention example problems that you can study. Okay, so reminding you that that's where the content is that you can read. Let's now go back to the video lecture where we summarize the key ideas. First, let me motivate the idea of acceleration. I'll remind you that in the previous video lecture, we introduced the concept of velocity. And I should be more specific. We introduced two kinds of velocity: average velocity and instantaneous velocity. However, both are, in a way, a measure of the rate of change of a particle's position. Rate of change of position. Average velocity measures that rate of change over a finite time interval. And by definition, it is the displacement a particle undertakes, delta x, in a finite time interval, delta t, divided by delta t. And instantaneous velocity is merely the average velocity expression in the limit as the time interval delta t vanishes towards zero. Okay, so loosely speaking, we say velocity accounts for the change in position of a particle. Can we not imagine scenarios where a particle's velocity changes? Not just its position, but its velocity. And we need a quantity that could measure changes in velocity, or to perhaps be more specific, rate of change of velocity. And that concept is called acceleration. An example of accelerated motion, where an object has a change in velocity that would be pertinent to this chapter, Chapter 2, Motion Along a Straight Line, would be one that I've mentioned before. Imagine an airplane sitting at rest at one end of the runway, waiting for its clearance to take off from the control tower. So its velocity while it's sitting there on the runway is, of course, zero. Once the airplane has clearance to take off, of course, what they do is they speed up, go faster and faster in the direction of the runway. And therefore, the speeding up represents a change in the airplane's velocity. And when the velocity of a particle changes, it has an acceleration. Now, that's not the only thing that can happen. Once a plane lands on a runway, then, of course, its task is to slow down. And that also represents a change of velocity, and that also represents an acceleration. We need to be able to deal with both kinds of scenarios. So let's get to our definition so that we can be specific when we talk about this concept of acceleration. So definitions first. Average acceleration. It is the rate of change of velocity over a finite time interval. I will remind you that average velocity was rate of change of position over a finite time interval. Now we're talking about rate of change of velocity over a finite time interval. The SI unit for average acceleration is the unit of velocity change divided by the unit of time, or time interval. Well, we know from the previous lecture that the unit of velocity, and therefore velocity change, is meter per second, and the unit of a time interval is second. So the SI unit of average acceleration, technically speaking, is meter per second per second. But one of the things you want to get used to is the fact that units obey the same rules of algebra as symbols. So meter per second is really meter divided by second squared, which we denote like this: meter over second squared, or meter per second squared. And that's how a physicist would say those units. The SI units of average acceleration are meters per second squared. What's the symbol for average acceleration? A for acceleration and a subscript AVG for average. Okay? All right, now, 3 lines means definition. Average acceleration is defined to be change in velocity, delta V, over change in time, delta T. And you'll see this written in your book and in other books as V2 minus V1 over T2 minus T1, where the way they want you to interpret that is the symbols, that the time interval begins at time T1 when the particle had velocity V1, and the time interval ends at time T2 when the particle had velocity V2. So the numerator V2 minus V1 is the change in the velocity, and the denominator T2 minus T1 is the change in time. Average acceleration, like average velocity, is a vector quantity, which means it has a magnitude and a direction. The direction will be denoted in this chapter merely by a sign, a positive sign, meaning it's directed in the plus x direction, or a negative sign, meaning it's directed in the negative x direction. Which sign, which direction the average acceleration has is determined solely by the sign or direction of delta V, the change in velocity, because that's the part of the definition of A average that determines whether A average is positive or negative. All right, that's really all I'm going to say at this point about average acceleration, other than then, if you are asked to calculate an average acceleration, this is what you should use: delta V over delta T, and presumably there is enough information given to you to figure out delta V over delta T. Or, turn that around a little bit, one could imagine a scenario where we tell you the average acceleration, and we tell you delta T, and we tell you V1 and ask for V2. Or we tell you V2 and ask for V1. It all just boils down to using that formula there that is the definition of average acceleration. There's really not much else you can do. That is the definition of average acceleration. Now, as you might imagine, there could be situations where you want to know the rate at which a particle's velocity is changing, not over a finite time interval delta t, but at an instant. Then you want what's called the instantaneous acceleration of the particle. That comes from the average acceleration in the limit as the time interval approaches 0. Same SI unit, instantaneous acceleration, as average acceleration, meter per second squared. What's the symbol or the notation? Just a lowercase italic a for acceleration. But it means instantaneous acceleration. It's defined to be, again, there's this mathematical process called a limit. As the time interval delta t goes to 0, and then this quantity that we're taking the limit of is the expression for average acceleration. then what I have next is just another way to write that expression inside the parentheses. The delta v, the change in velocity, v final minus v initial, is written like this. V initial means velocity at time t. V final means velocity at time t plus delta t. So the numerator is v final minus v initial. Just another way to write that. We divide by delta t. We take the limit as delta t goes to 0. The assumption is that limit is well defined and is finite. And whatever we get out from that, taking that limit, will be the acceleration of our particle at time t. That limit is called a derivative, and so everybody will write the shorthand version of all that limit notation like you see on the last bit here, dv over dt, which means the derivative of the velocity with respect to time. That is the definition of instantaneous acceleration. Let me say a few more comments about instantaneous acceleration, because there's a bit more to talk about to really fully understand it and then use it correctly to study the motion of particles. Okay, so as I just mentioned, we say that instantaneous acceleration is the derivative of velocity with respect to time. But since a derivative measures what's called a rate of change, the derivative of the velocity is also called, for short, the rate of change of the velocity. So you'll hear physicists say that acceleration is the rate of change of velocity for a particle. Now, if you recall when we studied instantaneous velocity as rate of change of position, we had a graphical way to interpret instantaneous velocity. If you give me a plot of position versus time, x versus t, the slope of the tangent line to that plot represents the instantaneous velocity of the particle. There's a similar meaning when we talk about acceleration. Now what you have to give me is a plot of velocity versus time for a particle. It's called a velocity time plot. And since acceleration is derivative of velocity, if you give me a plot of velocity versus time, acceleration is the slope of the tangent line to that plot. And that's very helpful to remember. The graphical representation of acceleration, instantaneous acceleration, is the slope of the tangent line on the velocity versus time plot. We're going to do a little bit of practice employing that graphical representation in just a minute. Here comes something else you'll see sometimes, and it's sometimes useful to remember. As we have just defined, instantaneous acceleration is the derivative of velocity with respect to time. As we saw in the previous lecture, instantaneous velocity is the derivative of the x position with respect to time. So let's combine these two ideas together. The instantaneous acceleration is the derivative with respect to time of the velocity, but the velocity is the derivative of x with respect to time. So what this means in calculus is to take the x function, it's a function of time, take one derivative of that with respect to time, and then whatever you get from that derivative, turn right around and take another derivative again. One derivative immediately followed by another. We call that a second derivative. So another way to think of instantaneous acceleration is that it is the second derivative of the position with respect to time. And we want shorthand notation for second derivative. And here it is. D superscript or exponent 2x over dt exponent 2. And there really is no good shorthand way to say that other than to just say it's the second derivative of x with respect to time, or t. And here's something very handy to remember. The second derivative of a function is a measure of what's called its concavity. And you can have no concavity, that's a straight line. It's kind of like curvature. You can have a function or a curve that's concave up, like a bowl, or a function that's concave down, like an upside down bowl. So concavity is a measure, if you like, of the kind of curvature of a function. The second derivative of a function is its concavity. It tells you its concavity. That is to say, if the second derivative of a function is positive, that function is concave up, like a bowl. If the second derivative of a function is negative, that function is concave down, like an inverted bowl. If the second derivative of a function is 0, it's a straight line. No curvature. So another way to think of instantaneous acceleration is second derivative of position with respect to time, and that means the concavity of the position versus time plot. All right, now, here's a little question to get your mind thinking. Go back in your mind to the previous video lecture. What does the direction of the instantaneous velocity tell you about a particle's motion? The direction of the instantaneous velocity v is either a positive, i.e. to the right, or negative, to the left. What is that sign of the instantaneous velocity telling you about the particle's motion? Why don't you think about that? Pause the video, think about it, see if you can come up with an answer, then come back. Okay, welcome back. Here's the answer to that question. Let's see, you can judge for yourself how close you got. The instantaneous velocity, the sign of it, positive or negative, at any given moment, tells you the direction the particle is moving. If the velocity is a positive number, then at that moment, the particle is moving in the positive x direction. If the velocity is a negative number, then at that moment, the particle is moving in the negative x direction. It is that simple. The direction of velocity is easy to interpret. The direction of the instantaneous acceleration is not so easy to interpret. It's a little bit more subtle. We're going to spend some time in class practicing with interpreting the sign of the acceleration. But for now, I'm just going to tell you two key things you really want to take to heart that will help you interpret what the sign of the particle's acceleration is telling you about its motion. Here we go. Statement number one. At a given moment in time, if the acceleration a and the velocity v have the same sign, either both positive or both negative, then we say the particle is speeding up while moving in the direction of the velocity. Speeding up is the operative phrase. If acceleration and velocity have the same sign, the particle is speeding up. Speeding up means the magnitude of its velocity, its speed, is getting bigger. If the particle had a little speedometer connected to it, that speedometer would be showing a larger and larger value. However, if the acceleration and the velocity have opposite signs, one of them is positive and the other one is negative, then the particle is slowing down while moving in the direction of the velocity. The magnitude of its velocity is getting less. It's slowing down. It's, if you like, coming closer to rest. Those two statements are key to remember, and we will use those to interpret the motion of a particle. We will use those two ideas a lot. But I will just warn you here of the trap that people fall into, a trap that is roughly half the time right and half the time wrong. The trap is this. So warning, what I'm about to say is not always correct. People sometimes believe that if the acceleration is positive, the particle is speeding up, and if the acceleration is negative, the particle is slowing down. Not necessarily, as we will see when we have our class session. What you've just got to remember is, if the acceleration and the velocity have the same sign, then it's speeding up. And if the acceleration and the velocity have opposite signs, then it's slowing down. Let's do a little mini application of that with graphs, of those ideas with graphs. In this little practice, we're going to look at a graphical representation of an elevator ride. So I want you to imagine a standard elevator cab in a building that's clearly going to travel vertically, and as you know, elevators travel vertically up and vertically down. Let's imagine a plus x-axis pointing vertically up. Okay? So motion vertically up is in the positive direction of that x-axis, and if the elevator is moving vertically down, that's in the negative direction of that x-axis. Okay, now what we have here are two plots. A velocity time plot is on top with velocity in meters per second versus time in seconds for an elevator. And then underneath that, we have an acceleration time plot with acceleration in meters per second squared versus time in seconds. Okay? And they're lined up vertically so that we can compare various regions of the graphs to each other. Let's start with the velocity time plot and interpret it, the graph, and think about the motion. Okay? So we have this first little interval right here between time 0 and 1 second where you can see the velocity curve is flat at a value of 0. Well, the value of 0 for velocity means the particle is not moving, it's at rest. So clearly, the elevator cab is at rest for the first second. Then it quickly but smoothly transitions to a velocity that's positive and getting bigger, right here, up to point B for a duration of 2 seconds. Then, from point B to point C, the velocity stays constant in the positive direction at 4 meters per second for a duration of 5 seconds. And then from point C down towards point D, the velocity is positive, but decreases down to 0. So clearly, the elevator is coming to rest, and then it stays at rest for that last second. So the velocity time plot tells a pretty clear story. The elevator starts at rest, speeds up going upward, travels at constant velocity going upward, then slows down going upward and stops, which is pretty standard behavior for an elevator going from one floor to another floor up above. Now let's compare the acceleration versus time plots. Remember, acceleration is derivative of velocity with respect to time, or rate of change of velocity. And acceleration is the slope of the tangent line on the velocity time curve. So everywhere on the velocity time curve, the slope of the tangent line is going to be equal to what the acceleration is. So for example, on that first 1 second, when the velocity is 0, the velocity curve is flat, horizontal. So the tangent line is horizontal, but the slope of a horizontal line is 0, so the acceleration is 0. So sure enough, right down here, for the first second, the acceleration value is 0. Then we transition to this linearly increasing positive velocity. So that's a straight line segment. The tangent line to that the tangent line is just another straight line. All I need to do to get the acceleration for this interval right up here is get the slope of that. Rise over run in the velocity time plot. It's clearly a positive slope, and the rise is 4 meters per second, and the run is 2 seconds, and 4 divided by 2 is 2. So the value of the acceleration for this 2-second interval when the elevator is speeding up is 2 meters per second squared constant, because a straight line is constant slope. Now how about the interval from point B to point C, when the velocity is constant at 4 meters per second? Well, then the velocity curve is flat, horizontal again. So the tangent line is horizontal, and the slope of a horizontal line is 0, so the acceleration is 0 again. So between points B and C, the acceleration value is constant at 0. Then we have the slowing down from point C downward. So now I look at that last downward sloping segment, and that's another straight line segment with a constant slope, but the slope now is negative. So the acceleration is going to be a negative value. And of course, slope is rise over run, so for that segment starting at point C and going downward, the rise is negative 4 meters per second, and the run is 1 second. Negative 4 divided by 1 is negative 4, so the acceleration now is negative 4 meters per second squared, and there it is down there. And then again, the velocity is constant at a value of 0, slope of the horizontal line is 0, the acceleration is 0 again. So you need to understand how we went from the velocity time curve to the acceleration time curve. You should, if given the velocity time curve, be able to draw the acceleration time curve on your own. Okay? Now, note in the speeding up phase, from t equals 1 second to t equals 3 seconds, the velocity is positive and the acceleration is positive. And as per our rule on the previous slide, if the velocity and acceleration have the same sign, the particle is speeding up. So in this first phase, the particle, the elevator, is speeding up. By the way, the little stick figures down below show you what you would feel. And the flattened person during the speeding up phase, going upward, means that you would feel like you were trying to be squashed a bit. We'll learn in later chapters why you feel that way. Now, in the slowing down phase, starting at point C on the velocity curve, the velocity is still positive. Yes, it's getting smaller, but it's positive. But the acceleration is a negative value. So in the slowing down phase, the velocity and the acceleration have opposite signs. The velocity is positive, the acceleration is negative. That means slowing down. That's exactly what the elevator is doing. And in that phase of the travel, you feel more stretched out. Okay? So that's an example of interpreting the motion of a particle from a velocity time curve and an acceleration time curve. And as I mentioned, if we gave you the velocity time curve, you should be able to draw that acceleration time curve for yourself with exactly the same level of detail as is shown here. Okay, so now what I want to do is I want to mention your class engagement exercise for this lecture. So here's what I want you to do. I want you to go to our Blackboard site for this class, and I want you to go into the discussion boards part. Let me show you what that looks like. I will go to our Blackboard site. So here what you see now is what it will look like. I have the instructor view, you'll have the student view, but here's more or less what you will see when you log into our Blackboard site for this course. And there you see it says discussion boards, and it's got discussion by video lecture and date, etc. And I'm about to give you the class engagement exercise that goes with video lecture 2.2. So to answer that, you would click on discussion video lecture 2.2. And it will open up that discussion topic with a little bit of a description. And then when you are ready to give the answer, you click here and you can either type your answer, or in this case, as you will see, I'm going to have you upload a file, and it's this little paper clip right here that will allow you to upload a file. All right, that's just showing you our Blackboard site, which you will be using a lot this semester. Now let me get back to these slides and let me tell you what I want you to do for the class engagement. I want you on a piece of paper, neatly, but by hand, sketch your own velocity time plot and acceleration time plot lined up vertically like you see on the screen here. But here's what I want you to do it for. An elevator that's traveling vertically downward. Just the opposite of the one we did here. I still want you to take a plus x axis going up, but now the elevator is going to go from one floor to the next floor below it. So it starts at a certain floor from rest. It will speed up traveling downward, then travel downward at a constant velocity, then slow down while traveling downward and come to rest and stop. I want you to plot the velocity time plot and the acceleration time plot that goes with that. Okay? You can assume the same general kind of behavior as you see here in terms of it takes 2 seconds to speed up, it travels 5 seconds at constant velocity, 1 second to slow down to a stop. Draw the velocity time plot and the acceleration time plot for an elevator that's traveling vertically downward from one floor to the next. Draw that, sketch those on a piece of paper neatly with as much detail as you see here. You'll need to presumably using your phone, take a photograph of it so that you can get an image, or even maybe better yet, a PDF that you can then save to your computer, or just using your phone, upload onto our discussion board on Blackboard. That is your engagement exercise for this video lecture. Now I have one more slide in this lecture to talk about briefly, and we will spend a good bit of time in class practicing with this. And now I'm going to continue with the concept of acceleration, but introduce a new section of reading, Chapter 2, Section 4, which is focused on a very special case. I can't emphasize too much how special we're talking about. A very special case, namely when a particle moves such that its velocity is what we call constant. Constant merely means that the acceleration a does not change with time. So what we're about to talk about is going to be a set of equations. I'm going to show you 3 of them that are very useful for studying the motion of a particle if that particle's acceleration is constant. I will tell you right up front, even though what I'm about to show you is a nice set of equations, one of the most common misuses of them is to apply them in a situation where a particle's acceleration is not constant, in which case you will get the incorrect answers. So you have to know, either because a problem you're trying to solve explicitly states that a particle's acceleration is constant, or perhaps more likely, and even more likely as you learn more physics, you have to be able to infer from the physics of the wording of the problem, or the wording of the problem's physics, that the acceleration of the particle is constant. The problem doesn't tell you. You have to be able to figure it out from the situation. But nevertheless, one way or another, let's imagine that you know that a particle is moving with constant acceleration. Then there's a set of equations that you can use that will help you study that motion. I'm going to show them to you now, and we will spend class time practicing with them. Here's the first one. It really just comes from the definition of average acceleration, right there. Remember, A average equals delta V divided by delta T. If the acceleration is constant, average acceleration and instantaneous acceleration are equal. The average acceleration is equal to whatever the acceleration is at any given time. So you can drop the AVG subscript on the A. And then just rearrange the formula. A equals delta V divided by delta T. So delta V equals A times delta T. And that's what these symbols are. And you have to be able to interpret them. The change in a particle's velocity is what delta V means. For a time interval, delta T is just the acceleration times delta T. You want to know how much a particle's velocity changes? Delta V. Just take the constant acceleration A times the amount of time, delta T. That's the form I like to start with, because that's the general idea. Change in velocity for a given time interval is just the constant acceleration times the size of the time interval. Now, a lot of books will take this formula and write it in a way that makes it look different, but it's really the same. It's just specialized one little bit. It's assuming that the time interval delta T starts when the clock reads 0, when T equals 0. Then the delta T, T final minus T initial, the T initial is 0, you can just use T for delta T. And the delta V means V final minus V initial. The V initial is written V subscript 0, because the initial time is 0. And then the minus V initial is taken over to the other side of the equal sign, and you get equation 1 here, shaded in blue. V final equals V initial plus AT. You take the initial velocity, the velocity at time 0, plus the acceleration times the value of the time, and that's the velocity at that time. That's what I call constant acceleration equation number 1. The simplest of them, in fact. You want to know where that one well, I really basically told you where that one comes from. But if you want to read more about the derivation of it, Chapter 2, Section 4 in your book. The next one is a little bit harder to derive, but your book does it. And I'm just going to tell you the result. Again, only valid if the particle is moving with constant acceleration. Here it is. You want to know how much a particle's position changes for a time interval delta t? You get it this way. You take the value that the particle's velocity was at the beginning of the time interval, v initial, times the amount of the time interval, delta t. But you have to add more onto it because the velocity is changing because there's an acceleration. You have to add to that 1/2 times the constant acceleration times the amount of the time interval squared. And I will tell you that with this equation, the most common mistake is to forget to square that factor of delta t. Now you will see this formula written in a slightly different way, based on the assumption that the time interval delta t begins at t equals 0. Then every delta t can just be replaced with a t, because t initial is 0. And that symbol v initial, the velocity at the beginning of the time interval, now means the velocity at time 0, and everybody writes that as v sub 0. Delta x means change in x final minus x initial, but x initial is now written x sub 0, and the minus x initial is now taken over to the other side of the equal sign, and then you get the second shaded equation, which I've numbered equation 2. X final equals x initial plus v initial t plus 1/2 at squared. And I call that constant acceleration equation number 2. And so now we have two useful equations that can be used to study the motion of a particle if we know the particle's acceleration is constant. One more of these that I'm going to talk about. Your book, by the way, if you read Chapter 2, Section 4, shows 5 equations, because you can derive more than the 3 here. But I have yet to find a problem in any physics textbook that I can't solve by using these 3. The third constant acceleration equation is based on a very simple thought. Constant acceleration equations 1 and 2 both involve the time variable, t. Either t to the 1 power or t squared. What if we have a problem, a scenario that we're studying, where the time for the motion is not known and is not asked for, yet the acceleration is constant? Wouldn't it be nice to have a constant acceleration equation that doesn't involve the variable t, time? No problem. Use equations 1 and 2 and get rid of t, the variable t. Take equation 1, solve it algebraically for the variable t. T will equal v final minus v initial all divided by a, and substitute that algebraic expression into equation 2 for the t and the t squared, and then simplify. You have to do the algebra carefully, but when you do, you get the third constant acceleration equation, and it no longer has the variable t. And here it is highlighted at the bottom of the screen. It says v final squared equals v initial squared plus 2 times a times the change in the position. No t. Okay? So, there will be homework problems that you will have where you need to use these equations. Quite a few of them, in fact. And we're going to be spending class time studying situations where a particle moves with constant acceleration. So these 3 equations will be very handy. You do want them to become your friend. You want to be very familiar with them. You want to be able to use them correctly. But remember, you can only use them when you know for sure that a particle's acceleration is constant. Okay, that is all for video lecture 2.2.